The story of Lord Kelvin begins not in the grand lecture halls of science, but in the quiet streets of Belfast, Ireland, where a young boy named William Thomson opened his eyes to a world teeming with curiosity. It was the early 1820s, an era when the Industrial Revolution was transforming human civilization, and yet nature still guarded her deepest mysteries. Born on June 26, 1824, William was the son of James Thomson, a mathematics professor, a man of discipline, intellect, and high expectations. From the very start, the child's mind seemed wired differently, as if tuned to the rhythm of unseen laws that governed the universe. His early years were not those of a typical boy. While others played in the streets, William sat beside his father, tracing equations on paper, watching how numbers could describe motion, how geometry could map the stars, and how logic could give form to wonder. When William was just 6, tragedy struck. His mother passed away, leaving his father to raise him and his siblings alone. The loss carved a quiet strength in the young boy's heart, a silent determination that would stay with him for life. His father, though stern, became both a teacher and a guide, introducing him to mathematics not as a school subject, but as a language, a way to speak to the universe itself. Their home in Glasgow, where the family later moved, became a living classroom. Books on mechanics, philosophy, and astronomy filled every shelf. At the dinner table, conversations about Newton's laws and the mysteries of heat replaced idle chatter. By the time William reached the age of 10, he had already surpassed the education of most adults. At 12, he entered the University of Glasgow, an age when most children are barely beginning secondary school. There, he walked among professors who were astonished at his comprehension and precision. He studied natural philosophy, chemistry, and mathematics, absorbing knowledge like a sponge. But beyond memorizing facts, he sought patterns, underlying principles that connected everything from planetary motion to the flicker of a candle flame. Even as a child, his notebooks revealed the soul of a thinker who believed that the universe was an elegant system, not a collection of chaos. His father's teaching style was strict, almost relentless, but it shaped William into a disciplined thinker. James Thomson believed in mental clarity and demanded perfection. He made his son repeat calculations until every digit was exact. This insistence on accuracy would later become one of Kelvin's defining traits, a belief that measurement was the foundation of all scientific truth. To measure was to understand, and to understand was to bring order to the unknown. At the University of Glasgow, William's brilliance soon became impossible to ignore. Professors began to treat him less as a student and more as a colleague. His essays showed not just knowledge but originality. One of his earliest works, written when he was only 15, analyzed the mathematics behind electricity and magnetism, a subject that was, at that time, barely understood. He was fascinated by how unseen forces could shape visible reality, and how abstract numbers could predict natural behavior. His young mind moved effortlessly between theory and imagination. Outside the classroom, Glasgow itself was a living laboratory. Steam engines hissed in the factories, telegraph wires stretched across the city, and invention was in the air. The young Thomson was surrounded by the pulse of progress. He watched engineers experimenting with iron and electricity, and he saw firsthand how the power of ideas could transform the world. Yet, he was not content with observing. He wanted to understand why these things worked. What invisible laws made them possible? When he turned 16, his academic path took a major turn. His father sent him to Cambridge University, the home of giants like Newton and Maxwell. There, at Peterhouse College, William found an environment that challenged and refined his genius. Cambridge was more than a school, it was a crucible of ideas. The air was thick with debate and discovery. Here, he encountered the mathematical rigor that would polish his mind into the tool of a true physicist. He threw himself into studies of calculus, geometry, and classical mechanics, often losing track of time, working late into the night with candlelight flickering on parchment. Unlike many students who sought prestige, William sought precision. His goal was not fame but truth. He was known for asking questions that cut straight to the heart of a problem. Simple yet profound questions that others had overlooked. What is heat, really? What does temperature measure? How can energy be described in numbers? These questions would later form the backbone of his life's work. But even in his student days, they hinted at the depth of his vision. At Cambridge, William's intellect didn't just flourish. It expanded beyond the classroom. He joined the university's rowing team, played the cornet, and took part in social gatherings. Despite his deep focus on science, he believed in the balance of mind and body. His friends admired his wit and good humor, often describing him as both humble and fiercely intelligent. He graduated in 1845, taking second place in the famous mathematical Tripos examination, a position that, in his eyes, was less than perfect. His lifelong pursuit of exactness made him dissatisfied with anything short of complete mastery, but it was during his time at Cambridge that a deeper transformation began. He discovered the works of Fourier, the French mathematician who had developed a theory of heat conduction. Fourier's ideas, elegant yet incomplete, sparked something in young Thomson's mind. He saw in them the possibility of uniting mathematics and physics into one coherent framework, a language through which energy itself could be understood. This encounter would define much of his future work. When William returned to Glasgow after his studies, he was only 22 years old. Yet, the university recognized his potential immediately, appointing him as the professor of natural philosophy, a position he would hold for more than 50 years. It was an extraordinary appointment for someone so young, but those who met him understood why. He spoke with the quiet authority of someone who not only knew science but lived it. His lectures were not mere lessons, they were performances of logic and wonder. He used instruments, experiments, and stories to bring abstract theories to life, showing students that physics was not a cold set of formulas, but the poetry of the natural world written in the language of mathematics. Even as a young professor, his dedication bordered on obsession. He would spend entire nights in his laboratory, adjusting instruments, taking measurements, and scribbling equations in a frenzy of inspiration. His mind seemed incapable of rest. Every question led to another, every discovery opened a new door, yet, behind this relentless drive was a sense of humility, a belief that nature's secrets could only be revealed to those who sought them with patience and precision. In these early years, Kelvin's identity as a scientist took shape. He learned that brilliance alone was not enough. Discipline and clarity were the true companions of genius. He also learned that education was not about memorization, but about awakening the capacity to think independently. His own journey, from the quiet home lessons with his father to the halls of Cambridge and Glasgow, was proof that the greatest education begins with curiosity. The young William Thomson's story was not one of sudden fame, but of gradual evolution. Every stage of his early life prepared him for the discoveries that would later define his name. His childhood trained his precision, his university years shaped his intellect, and his early professorship honed his creativity. He had all the qualities of a pioneer, a tireless work ethic, an unshakable belief in the power of numbers, and an unending curiosity about how the universe functioned at its most fundamental level. By the time he stood before his first class as Professor Thomson, the seeds of greatness had already been sown. His mind was ready to tackle the mysteries of heat, energy, and motion, concepts that would one day lead him to define the very limits of temperature itself. The world had yet to know him as Lord Kelvin, the man who gave science its absolute zero, but the young William was already walking the path that would lead him there. In the quiet glow of a gas lamp, surrounded by instruments and equations, he began to sketch ideas that would later change the world. Each equation was a step toward understanding, each experiment a window into the invisible. His early education had not merely taught him knowledge, it had given him a vision of a universe ruled not by mystery, but by measurable, elegant order, and that belief, formed in the classroom of his father and tested in the universities of Britain, would become the foundation upon which the rest of his life's work would stand. The story of Kelvin's early brilliance is, in truth, a story about the power of nurture, curiosity, and discipline working together. It shows how the spark of genius, when guided by structure and fueled by wonder, can illuminate the darkest corners of knowledge. His journey from a child prodigy in Belfast to a young professor in Glasgow is not just the tale of one man. It is a reflection of the spirit of science itself, the human desire to understand, to measure, and to bring order to the chaos of the unknown. As the first light of morning crept through the Glasgow windows of his study, young Professor Thomson would often look up from his papers, his eyes glowing with the satisfaction of discovery. Around him lay the scattered notes of a mind already touching the edges of the infinite. He may not have known it then, but history would one day remember him as the man who measured the immeasurable, the mind that defined absolute zero. As the years unfolded at the University of Glasgow, William Thomson's reputation grew quietly but steadily. His lectures were unlike anything the students had ever seen. In dimly lit rooms filled with the smell of chalk and brass instruments, he would draw sweeping curves on blackboards, his voice calm yet charged with conviction. The young professor spoke not from the authority of titles, but from a deep intimacy with the laws he described. When he demonstrated the properties of heat using simple metal rods or spoke of invisible forces that traveled through the ether, students felt as if they were standing at the edge of a great revelation. Every lecture was an invitation to see nature not as a mystery, but as an intelligible system, waiting for minds precise enough to measure it. In these early professional years, Thomson's own education did not stop. He read endlessly: Faraday, Carnot, Fourier, Newton, and he experimented as obsessively as he studied. His small laboratory became a sanctuary of instruments, thermometers, galvanometers, delicate coils of copper, mirrors, and pendulums. He built his own devices when none existed, shaping brass and glass with his hands until they obeyed the needs of his experiments. Through this ceaseless tinkering, he discovered that the act of building was itself a form of learning. Every screw and lens carried a lesson, every error a whisper of a deeper truth. The world around him was also learning, though in fits and starts. Science in the mid-19th century was fragmentary. Physics, chemistry, and engineering were separate realms whose languages barely overlapped. Thomson believed they should speak one dialect. Mathematics, numbers, to him, were not abstractions but the grammar of creation. This conviction, born from his early education under his father and matured at Cambridge, began to crystallize into a philosophy: measurement as the heart of knowledge. It was not enough to describe phenomena, one must quantify them. He insisted that without numbers, understanding was only a shadow of truth. His insistence on rigor sometimes intimidated his students and colleagues. They called him precise to the point of obsession. Yet that precision came from a place of wonder. When he calculated, he was not chasing perfection for its own sake. He was listening for the subtle harmonies of the universe. In his notes from these years, one can sense the rhythm of discovery lie. The quick sketches of apparatus, the fine lined graphs, the tidy proofs that unfold like music written in equations. Each page reveals the mind of a man who saw beauty in balance and order. By his late 20s, Thomson had begun corresponding with other great scientists of the age: Faraday in London, Joule in Manchester, Helmholtz in Germany. Letters traveled slowly, yet their content was electric. Through these exchanges, he sharpened his ideas about heat and energy, topics that had captured his attention since his youth. The world had steam engines, but not yet thermodynamics. The question burning in his mind was one that would shape modern physics: how does energy transform, and can any process ever be perfectly efficient? The roots of that question lay in his earliest fascination with numbers and nature's limits, cultivated by years of disciplined education. The seed his father planted was now sprouting into a theory that would redefine science. The habits of his formative years also influenced how he approached collaboration. Unlike many academics of his time, Kelvin welcomed the partnership of engineers, mechanics, and artisans. He respected the craftsman's touch as much as the mathematician's proof. This openness stemmed from the practicality he had observed in Glasgow's industrial streets as a boy. Knowledge, he believed, should serve humanity, not merely decorate bookshelves. Every wire he coiled, every equation he derived, carried within it the conviction that science was a tool for progress. Still, even a mind as brilliant as Kelvin's needed humility. The challenges he faced in reconciling theory with experiment often humbled him. Instruments failed, equations misbehaved, results contradicted expectations. But those failures became his tutors. He once wrote that, "Mistakes are the portals of discovery," a sentiment that reveals the patience of his intellect. When an experiment collapsed, he returned to his notes with renewed focus, analyzing every step, adjusting variables, and trying again until the data aligned. This persistence mirrored the rigorous discipline of his childhood, his father's insistence that one correct every calculation until it was flawless. The echo of those early lessons guided him through the labyrinth of research. As his prestige grew, invitations arrived from across Europe. He traveled to Paris, meeting with French scientists who admired his mastery of mathematics, and to Germany, where physicists were wrestling with the same questions of heat and work. These journeys expanded his intellectual horizon. He witnessed how other nations fostered scientific inquiry through academies, salons, and vast laboratories. Back in Britain, he advocated for the same unity between pure science and applied technology, arguing that education should cultivate both imagination and precision. This belief was not abstract idealism, it was the direct extension of his own life story. His early brilliance had flourished because his education had balanced theory and practice. He now sought to give that balance to others. During these years, Kelvin's personality matured as well. The boy who once competed with himself for perfect answers evolved into a mentor who inspired others to question. He still demanded accuracy, but had learned the value of curiosity without fear. Students recalled how his eyes would gleam when someone proposed a bold idea, even if it was wrong. "A wrong idea," he would say, "is closer to truth than no idea at all." Such moments reveal a gentler dimension of his intellect, one shaped by reflection and empathy, not merely logic. His social circle widened beyond academia. He attended gatherings with inventors, shipbuilders, and businessmen, exploring how physics could aid navigation and communication. These interactions sowed the seeds of his later achievements with the transatlantic telegraph. But in these early stages, what mattered most was learning. Every conversation was a new form of education. Kelvin treated the world itself as a classroom, and life as a continuous lesson in understanding the laws that govern both nature and human endeavor. In quiet hours, when lectures were done and instruments silent, he often returned to contemplation. Friends recalled seeing him stare out over the River Clyde, lost in thought, as if calculating the invisible currents of the world. It was in such moments that his philosophical side emerged. For Kelvin, knowledge was not merely about control or prediction, it was about communion with the order of creation. His faith and his science coexisted peacefully. The universe, in his view, was a grand design of rational beauty, and by studying it, humanity honored its creator. This spiritual undertone, shaped by his upbringing, infused his scientific work with purpose. The progress of his career mirrored the maturing of Victorian science itself. Britain was becoming the workshop of the world, and precision instruments were in high demand. Kelvin's insistence on exact measurement inspired a generation of engineers to improve their tools. Thermometers, barometers, and galvanometers became more accurate under his influence. His teaching spread through apprentices and colleagues who carried his methods into new laboratories. Thus, the education he had once received now radiated outward, multiplying itself through others. The cycle of learning continued, from father to son, from teacher to student, from idea to innovation. Yet the pressure of expectation weighed heavily on him. The young prodigy had become a national figure, and with fame came scrutiny. Critics challenged his theories, rivals competed for recognition. Kelvin's response was always the same: more work, deeper thought, better proof. When disputes arose, he did not argue through rhetoric but through data. He believed that nature herself was the final judge, and that accurate experiment would silence all disagreement. This scientific integrity, born from his earliest lessons in honesty and discipline, earned him respect even among opponents. The late 1840s and early 1850s were a time of creative storm. Kelvin published papers on the flow of heat, on elasticity, and on electricity. Each one was dense with mathematics yet alive with physical insight. Behind every line lay hours of reflection and years of training. When he wrote about heat conduction, he saw more than formulas. He envisioned the dance of molecules, the invisible exchange of energy that made the world function. His education had given him the rare ability to think simultaneously like a mathematician, an engineer, and a philosopher. That synthesis would define his legacy. As the seasons turned and decades shifted, the young professor matured into the scientist history would call Lord Kelvin. But the transformation was gradual, rooted deeply in the foundation of his formative years. The habits of precision, the joy of problem solving, the resilience learned from failure, all remained constant. Even when honored with titles and fame, he often spoke with nostalgia about his father's lessons and his student days at Glasgow and Cambridge. Those memories reminded him that every discovery began with curiosity and discipline intertwined. The true brilliance of Kelvin's early education lies not only in what he learned, but in how he learned to learn. He approached knowledge as an endless horizon. No fact was final, no theory complete. This humility kept his mind alive well into old age. It also shaped the very culture of physics. Generations after him would inherit the notion that science advances not by dogma, but by continuous questioning grounded in measurement. By the end of his early phase, before the great discoveries that would define his later life, Kelvin had already achieved what many never reach: intellectual maturity. He had forged a method of inquiry built on precision and imagination, discipline and wonder. His life up to that point was a testament to the power of education when guided by passion. He proved that learning is not confined to classrooms. It is a lifelong pursuit that deepens with each observation, each calculation, each quiet moment of thought. As the evening sun set behind the towers of the University of Glasgow, the glow of the gas lamps flickered across the windows of his laboratory. Inside, the professor worked alone, his pen moving rhythmically across the paper. Equations formed like constellations, linking ideas across time and space. Outside, the city hummed with the sounds of industry, the very energy he sought to understand. In that solitude, surrounded by instruments and the faint ticking of clocks, one could glimpse the culmination of all that his early life had built, the mind of a man prepared to measure the universe itself. He paused for a moment, gazing at a thermometer on his desk. To others, it was a simple tool. To him, it was the symbol of a lifelong journey, from a child fascinated by numbers to a scientist who would one day define the scale by which temperature is known. Every degree marked not just a physical value, but a step on the path of learning. His education had taught him that understanding begins with curiosity, but it achieves greatness through precision. That realization would soon lead him to the concept that would make his name immortal: absolute zero. The night deepened, the pen stopped, and silence filled the room, yet within that silence the echo of his early brilliance lingered. It was the sound of a young mind that had transformed discipline into discovery and education into enlightenment. The boy from Belfast, shaped by a father's guidance and a lifetime of relentless curiosity, had become something more than a scholar. He had become a measure of human potential itself, the embodiment of how knowledge, when pursued with heart and intellect united, can illuminate the coldest reaches of the unknown. In the quiet laboratories of the University of Glasgow, the soft hiss of boiling water and the faint shimmer of heated metal filled the air. Here, amidst the scent of oil lamps and the scattered notes of mathematics, William Thomson's fascination with heat began to take shape. To most people, heat was an everyday experience. The comfort of a fire, the power of a steam engine, the warmth of sunlight. But to Thomson, it was something more mysterious, something that pulsed through the very fabric of the universe. He saw heat not merely as a feeling, but as a form of motion, an invisible dialogue between energy and matter. From the earliest days of his research, he sensed that within this ordinary phenomenon lay the key to understanding nature's most profound laws. The Industrial Revolution was in full swing. Steam engines powered ships and factories, propelling nations into a new age of production. Yet, even as these machines drove progress, the science behind them remained incomplete. Inventors knew how to make engines work, but few understood why they worked. What happened when water turned into steam? What did heat actually do? Could it be created or destroyed, or was it something that merely moved from place to place? These questions hovered in the air of every workshop and laboratory in Europe. For William Thomson, they became an obsession. His interest in the subject had been sparked years earlier when he read the writings of the French mathematician Joseph Fourier. Fourier had proposed that heat flowed through materials in a predictable way, governed by mathematical laws. His ideas were revolutionary, but they lacked full physical interpretation. To many, they were abstract, detached from real engines and experiments. Yet to Thomson, Fourier's equations were like music, patterns that hinted at an underlying order. He believed that by understanding the flow of heat, one could uncover universal principles governing all forms of energy. It was this conviction that ignited his lifelong pursuit. When Thomson returned to Glasgow as a young professor, his laboratory became a stage for his growing curiosity. He conducted experiments with bars of iron, columns of water, and plates of glass, observing how heat spread, how temperature changed over time, and how energy seemed to transform from one form to another. He began to suspect that heat and motion were not separate things at all, but different expressions of the same fundamental reality. Each time a metal rod warmed, molecules were vibrating faster. Each time a steam engine roared, invisible particles danced in greater frenzy. To him, heat was motion itself, and that realization would soon change physics forever. Around this time, the ideas of Sadi Carnot, a French engineer, began to resurface. Carnot had proposed that there was a theoretical limit to how efficiently any engine could convert heat into work. His work, rediscovered after his death, suggested that heat moved in cycles from hot to cold, and that no engine could ever be perfectly efficient. When Thomson encountered Carnot's writings, they struck him like a revelation. He realized that Carnot's heat engine was not just a machine but a metaphor for the universe. Everything in nature, from the burning of the sun to the beating of a human heart, operated according to the same principle, energy flowing from higher to lower states. But the world of science was divided. Some believed that heat was a kind of fluid, a weightless substance called caloric that flowed from one body to another. Others, like James Joule, were beginning to prove that heat was not a fluid at all, but a form of motion, interchangeable with mechanical work. In Manchester, Joule's careful experiments showed that when mechanical energy was used to stir water, the water's temperature rose. Motion could become heat. Energy could change form. The implication was staggering. It meant that the universe was governed by conservation, not consumption. Energy could never be lost, it only transformed. Thomson, ever the cautious thinker, did not accept Joule's conclusions immediately. His education had trained him to balance imagination with skepticism. For months, he pored over Joule's data, repeating calculations and designing his own tests. He wanted proof beyond doubt. Gradually, the numbers began to speak. The mechanical equivalent of heat. The precise amount of work needed to produce a given quantity of heat emerged as a measurable constant. This discovery united the physical and the mechanical worlds. Heat was energy, and energy was eternal. For Thomson, the elegance of this realization was breathtaking. It was as if he had glimpsed the heartbeat of the cosmos. From this point on, his fascination turned into devotion. Every thought, every experiment seemed to circle back to the mysteries of heat and energy. He began to explore how temperature could be defined not in arbitrary human terms like Celsius or Fahrenheit, but in absolute terms, terms grounded in the very behavior of matter itself. Temperature, he believed, should reflect the true state of motion among particles. He started developing the mathematical framework for what would become the absolute temperature scale. In this system, there would exist a point of perfect stillness, a state where molecular motion completely ceased, absolute zero. The idea was radical, almost poetic, that there existed a limit to cold, a silent edge beyond which motion could not go. But this insight did not come overnight. Thomson wrestled with it for years, constantly refining his equations and testing his assumptions. He debated with colleagues, some of whom thought the concept of absolute zero was purely theoretical. Yet Thomson persisted. The deeper he went, the more he felt that temperature and energy were two sides of the same coin. Every degree of heat corresponded to a measurable quantity of motion. Every change in energy reflected a change in temperature. This unification of concepts became the foundation of thermodynamics, the science of energy transformation, and Thomson was among its chief architects. The fascination that drove him was not cold logic alone, it was curiosity of the highest order. He saw beauty in the invisible. Where others saw only the glow of a fire, he saw the ceaseless dance of particles, the conversion of chemical potential into radiant energy. When a kettle boiled, he did not merely hear the sound of steam, but imagined the frantic collisions of molecules at the microscopic level. To him, heat was the song of motion, the universe humming with energy. That vision transformed ordinary experiences into scientific revelations. Thomson's work was not confined to theory. He understood that true knowledge required instruments capable of precision. He designed and refined thermometers, galvanometers, and measuring devices that could detect the smallest fluctuations of temperature and voltage. His inventions allowed scientists to quantify what had previously been beyond reach. These tools became the foundation for countless discoveries in physics and engineering. Through them, the abstract notion of energy became something measurable, tangible, real. By the mid-19th century, Thomson's research had begun to reshape the way science viewed the world. His papers on the dynamical theory of heat and on the mechanical equivalent of heat established a new framework for understanding nature. He showed that every natural process involved the conversion of energy from one form to another, and that in every such process, some energy was always lost to entropy, an unavoidable increase in disorder. This insight carried both scientific and philosophical weight. It suggested that while energy could never be destroyed, the universe itself might be moving toward a state of equilibrium, a cosmic stillness that echoed his notion of absolute zero. As these ideas matured, Thomson's fascination deepened into reverence. He began to see energy not merely as a property of matter, but as the essence of existence. The world, he believed, was an endless interplay of transformations. Mechanical work becoming heat, heat becoming motion, motion radiating into light. The same forces that powered the steam engine also governed the stars. From the smallest atom to the largest galaxy, the principle was universal. To him, this unity of nature was both a scientific truth and a spiritual revelation. He often spoke of the beauty of the Creator's design, a phrase that revealed how deeply intertwined his faith and his physics had become. Behind the calm exterior of the professor was a restless mind that never stopped questioning. Night after night, he worked by the dim light of candles, surrounded by thermometers and metal rods, jotting figures into his worn notebooks. The room would grow warm with the heat of the experiments, yet in his mind, he was always chasing the concept of cold, the limit beyond which motion ceased. It was a paradox. He loved to understand heat, one must also understand the absence of it. And so he calculated, imagined, and experimented, always searching for that perfect balance between theory and nature. His fascination also extended beyond the laboratory to the great engines of the world. He studied steamships, industrial boilers, and telegraph systems, analyzing how energy efficiency could be improved. For him, understanding heat was not just an academic pursuit, it was a way to make human progress more harmonious with natural law. He believed that by mastering energy, humanity could achieve greater control over its destiny. This belief was not arrogance but hope. A hope born from his deep respect for the order of nature. As he continued to refine his understanding of thermodynamics, Thomson's correspondence with Joule evolved into collaboration. The two men, one experimentalist, one theoretician, complemented each other perfectly. Joule's experiments provided data. Thomson's equations provided interpretation. Together, they formulated the Joule-Thomson effect, describing how gases change temperature when they expand without exchanging heat. This discovery not only advanced physics, but also found practical applications in refrigeration and industry. It was a perfect example of how curiosity could lead from abstract theory to tangible progress. By now, Thomson's life had become an intricate weave of thought and experiment. His fascination with heat was no longer just a subject of study. It was the axis around which his entire worldview revolved. He saw energy as the common thread connecting mechanics, chemistry, electricity, and even life itself. Every living organism, every burning star, every moving machine participated in the same eternal exchange. It was a revelation that blurred the boundaries between science and philosophy, showing that the laws of physics were also the laws of existence. When he walked through the university courtyard in the chill of a Glasgow winter, his breath rising like vapor, he would sometimes pause to observe the frost forming on the stones. To others, it was merely a sign of cold. To Thomson, it was nature's demonstration of order emerging from motion, slowing to stillness, a whisper of absolute zero. The fascination that had begun in his youth had now become a lifelong meditation. It guided every calculation he made and every lecture he gave. In his students' eyes, he was not merely a physicist but a seeker, a man trying to read the invisible scripture of the universe. He often told them, "The study of heat is the study of life." For in understanding energy, its transformations, its limits, its persistence, one comes closest to understanding existence itself. The warmth of the sun, the burning of coal, the beating of the heart, all were chapters of the same story. And it was this story that William Thomson, soon to be known as Lord Kelvin, dedicated his life to telling through numbers, instruments, and unyielding curiosity. As Lord Kelvin's fascination with heat and energy deepened, so too did his desire to find the hidden language that governed the physical world. He was no longer simply a mathematician intrigued by numbers. He had evolved into a thinker who sought to understand the heartbeat of nature itself. The 19th century was a time of industrial expansion, filled with roaring engines, smoke, stained skies, and the ceaseless hum of progress. Yet beneath that surface of invention, the science of energy, what would later be known as thermodynamics, was still young and uncertain. Many believed heat to be a kind of invisible fluid called caloric, while others thought of it as a mysterious substance that flowed from hot bodies to cold ones. Kelvin entered this world of confusion with a determination to bring clarity and order, to uncover the laws that connected motion, temperature, and the very structure of the universe. In the laboratories of Glasgow, Kelvin's experiments were not grand spectacles of fire and explosions, but careful, methodical measurements. He observed how metals expanded when heated, how gases changed under pressure, and how energy could shift forms without ever disappearing. These experiments, though simple in appearance, were windows into the deepest truths of matter. Kelvin understood that to explain energy, one had to measure it, and to measure it, one had to define it. Every calculation, every adjustment, every observation brought him closer to seeing nature not as chaos, but as a system of elegant and consistent principles. His studies were not limited to his own findings. Kelvin immersed himself in the discoveries of his contemporaries. He followed closely the works of James Prescott Joule, a young physicist who demonstrated that mechanical work could be converted into heat. Joule's experiments suggested that energy was conserved, not lost, a revelation that fascinated Kelvin. The two men eventually met, and their collaboration became one of the great scientific partnerships of the century. Together, they explored how mechanical motion and thermal energy were two expressions of the same underlying phenomenon. It was during these studies that Kelvin began shaping what would become the second law of thermodynamics, a law that revealed the direction of time itself, showing that energy naturally flows from order to disorder, from heat to cold, from motion to stillness. Kelvin's fascination with heat extended far beyond the laboratory. He imagined the cosmos as a grand machine governed by the same laws that applied in his experiments. He proposed that the universe, like a great clock, was winding down toward a final state of equilibrium, a point when all energy would be evenly distributed and motion would cease. This idea, often referred to as the heat death of the universe, was both scientific and philosophical. It forced humanity to confront the reality that even the stars, blazing symbols of eternity, might one day fade into silence. Kelvin did not see this as despair, but as truth, a mathematical poetry written into the structure of existence. His lectures on thermodynamics captured the imagination of both scientists and students. In his precise yet passionate voice, he described the transformation of heat into motion and the delicate balance of nature's energy. Those who attended his lectures often remarked that he had the rare ability to make the invisible visible. When he spoke of atoms vibrating in heat, of gases expanding into emptiness, or of the deep coldness of space, his audience could almost feel those forces at work. For Kelvin, teaching was not merely the transmission of facts, it was an act of awakening. He wanted others to feel the same wonder he felt when he looked at a flickering flame and saw the mathematics of the cosmos behind it. Kelvin's investigations were grounded in practical innovation as much as theoretical thought. He built instruments that could measure temperature more precisely than ever before, including delicate thermometers capable of detecting minute differences in heat. His methods of calibration and his insistence on accuracy became legendary. He once remarked that science advances not just through grand theories, but through the perfection of measurement. To Kelvin, every degree, every number mattered. It was the bridge between human perception and the physical truth of the world. His reputation grew rapidly, not only in academic circles, but also among engineers, inventors, and industrialists. The world was entering an age powered by steam and electricity, and Kelvin's insights into energy were helping to make that transition possible. He advised on the improvement of steam engines, making them more efficient and less wasteful. He showed how understanding the flow of heat could lead to better machines, better power systems, and even better communication networks. The same curiosity that led him to study the laws of nature now guided him in shaping the future of technology. In his discussions on heat, Kelvin often returned to a single theme: the unity of nature's forces. He believed that all forms of energy, whether thermal, mechanical, or electrical, were interconnected. To him, understanding heat was the key to understanding everything. This belief gave birth to his famous concept of the absolute temperature scale, where 0 represented the total absence of heat and molecular motion. For Kelvin, this was not just a mathematical curiosity, it was a symbol of perfection, a universal constant that applied everywhere, from the surface of the Earth to the farthest reaches of space. The idea of absolute 0 fascinated both scientists and philosophers alike. It suggested that there was a limit to coldness, a boundary where nature's dance came to rest. In that motionless silence, Kelvin saw the purity of physics, an ultimate truth that could only be approached, never reached. His thoughts on absolute 0 inspired countless experiments in low-temperature physics, eventually leading to the discovery of new states of matter. Though he could not have imagined technologies like superconductivity or quantum refrigeration, his ideas laid the groundwork for them. Kelvin's fascination with energy was not confined to the laboratory or the lecture hall. It was a lifelong companion. Even in his later years, as his beard turned white and his hands trembled slightly from age, his mind remained sharp and curious. He often spoke of how the laws of heat were not just mechanical but deeply philosophical. To him, studying energy was studying existence itself, the flow of heat, the transformation of motion, the fading of stars. All were part of a grand narrative that revealed both the beauty and the fragility of the cosmos. In his correspondence with other scientists, Kelvin often debated the nature of energy, entropy, and time. These discussions were sometimes intense, even controversial, but always rooted in respect and intellectual honesty. He was known for challenging ideas without dismissing them, for questioning assumptions without arrogance. His scientific mind was both disciplined and creative, blending the precision of mathematics with the imagination of a poet. He once said that science was not a cold pursuit, but a living dialogue with nature, a conversation between the measurable and the mysterious. As the world changed around him, electric lights replacing gas lamps, telegraph cables shrinking the oceans, factories transforming cities, Kelvin saw these not just as technological marvels, but as reflections of the laws he had spent his life uncovering. Every engine that turned, every current that flowed, every signal that traveled across a wire was an echo of the principles he had devoted his career to understanding. For him, energy was not simply a resource, it was the pulse of creation. Toward the end of his life, Kelvin often looked back at his years of study with humility. He admitted that the more he learned about heat and energy, the more he realized how vast the unknown truly was. The mysteries of the universe, he believed, were infinite, and each discovery only deepened his sense of wonder. Yet there was satisfaction too, a quiet pride in knowing that his work had given humanity a language to describe the invisible forces that govern existence. When Lord Kelvin passed away in 1907, the world lost more than a scientist, it lost a philosopher of nature, a man whose mind had bridged the gap between theory and reality. His fascination with heat and energy had not only advanced physics, but had transformed how humans viewed the universe. The laws he helped define became cornerstones of modern science, shaping everything from industrial technology to cosmology. Even now, when scientists speak of energy conservation, entropy, or absolute zero, they are echoing the legacy of the man who first saw order in the dance of heat and motion. Lord Kelvin's fascination with energy remains timeless. It was not merely an academic pursuit. It was a reflection of humanity's endless curiosity. His life reminds us that every spark of inspiration, every question about how the world works, can lead to truths that define generations. Through his work, Kelvin revealed that understanding the invisible forces of nature is not just science. It is a form of art, a testament to the power of the human mind to grasp the infinite. The story of the absolute temperature scale begins not in a laboratory filled with advanced instruments, but in the restless mind of a man who believed that the secrets of nature could be revealed through logic and precision. Lord Kelvin, driven by an insatiable curiosity, stood at a point in history when science was transitioning from philosophical speculation to exact measurement. The mid-19th century was an era when the world was learning to measure itself: time, light, distance, pressure, and now, temperature. Yet the existing temperature scales, such as Celsius and Fahrenheit, were based not on universal laws, but on human conventions: frozen water, boiling water, and arbitrary points in between. For a mind like Kelvin's, these were insufficient. He sought a system not built on convenience, but on the very laws that governed the universe itself. As he pondered the mysteries of heat, Kelvin realized that temperature was not merely a sensation or a number on a scale. It was a reflection of the internal motion of particles, the very rhythm of matter. The warmth of a flame, the chill of ice, the cold of space, all were part of a grand continuum. He began to ask a simple yet profound question: what happens as heat is removed from a substance? Does temperature go on decreasing forever, Or is there a limit beyond which cold cannot exist? It was a question that no thermometer of his time could answer, for it required a new understanding of what temperature truly meant. Kelvin's inspiration came partly from the work of French physicist Sadi Carnot, who had studied how heat engines worked. Carnot had proposed that heat was a kind of energy that could be converted into mechanical work, and that there were natural limits to this conversion. Kelvin found in Carnot's ideas the foundation of a new concept, a scale of temperature that would not depend on the properties of any specific material, but on the laws of thermodynamics themselves. He imagined a scale that began not with water or air, but with pure physical meaning, a scale that started at the point where molecular motion completely stopped. In 1848, William Thomson, who would later become Lord Kelvin, published a paper titled On an Absolute Thermometric Scale founded on Carnot's theory of the motive power of heat. In it, he proposed a revolutionary idea, a temperature scale in which 0 represented a state of absolute cold, a point where no further energy could be extracted from matter. This was the birth of the Kelvin scale, a universal measurement rooted not in human experience, but in the nature of reality itself. Kelvin's absolute zero, calculated to be 273.5 degrees C, marked the boundary between motion and stillness, between energy and emptiness. To Kelvin, this was not just a numerical curiosity. It was a doorway into understanding the universe. He realized that if temperature could be tied to energy, then every physical process, from the boiling of water to the cooling of a star, could be described in terms of the transfer of heat. This insight unified the study of thermodynamics, linking the smallest movements of atoms to the vast dynamics of cosmic systems. His absolute scale offered a common language through which scientists could describe both laboratory experiments and celestial phenomena. Kelvin's mind saw beauty in precision. He believed that the universe operated according to mathematical laws, and that by defining these laws, humanity could reveal the hidden order of existence. The absolute scale, for him, was a symbol of that order, a perfect measure untouched by the imperfections of human perception. Unlike Celsius or Fahrenheit, which were bound to the properties of water or air, the Kelvin scale existed independently of any substance. It was the purest possible expression of thermal reality. As his concept took shape, Kelvin began to explore its implications. If 0 on his scale represented the total absence of heat, what would the upper limits look like? Was there such a thing as infinite temperature? Could energy exist without limit? These questions pushed the boundaries of classical physics. Kelvin speculated about the immense energies within the stars, the slow cooling of the Earth, and the eventual destiny of the universe. He saw temperature not as an isolated property, but as a universal variable, one that connected chemistry, physics, and cosmology in a single thread. In his lectures, Kelvin described absolute zero with a mixture of scientific rigor and poetic awe. He spoke of atoms that would cease to move, of a silence so deep that even the vibrations of existence would stop. His audience, accustomed to thinking of heat in everyday terms, began to see it in a new light, as a manifestation of motion, of life itself. Kelvin's words had a way of transforming equations into visions. He made the invisible visible, turning the abstract idea of temperature into a tangible window into the structure of the universe. The practical applications of his scale soon became evident. Scientists and engineers began using the Kelvin system to measure temperature in experiments that required accuracy beyond what traditional thermometers could offer. In the study of gases, where small changes in temperature could mean vast changes in pressure, Kelvin's scale provided consistency. In the emerging field of cryogenics, where materials were cooled to extreme lows, it became essential. Even in astronomy, where scientists sought to understand the heat of stars and the cold of space, Kelvin's absolute temperature became the language of the cosmos. But Kelvin's fascination with absolute zero was more than technical, it was philosophical. He recognized that the idea of a limit to coldness had profound implications for how we understand energy and time. As matter approaches absolute zero, motion ceases, and with it, the flow of time itself seems to slow. Kelvin's thoughts foreshadowed ideas that would later become central to quantum physics and cosmology. He imagined a universe governed by energy transformations, with absolute zero as the final stillness, the ultimate equilibrium. This pursuit of absolute measurement reflected Kelvin's broader belief in the unity of science. He often said that the true goal of physics was to express the laws of nature in universal terms, numbers and constants that would be true everywhere, from the laboratory to the stars. The Kelvin scale was one of the purest realizations of that dream. It was a scale that did not rely on the accidents of human design, but on the fundamental structure of reality. In creating it, Kelvin gave science a tool that could stand the test of time, one that remains in use more than a century later. In the quiet of his study, surrounded by stacks of notes and equations, Kelvin often reflected on the journey that had brought him to this point. From the young prodigy fascinated by the flow of heat to the mature scientist defining the limits of the physical world, he had traveled from curiosity to revelation. The absolute scale was more than a scientific achievement. It was a culmination of a lifetime's thought. It represented the bridge between the tangible and the abstract, between experiment and theory, between the known and the infinite. His friends and colleagues admired his brilliance, though few could match his intensity. They spoke of how Kelvin could move seamlessly between mathematical abstraction and practical engineering. One moment, he would be discussing the laws of thermodynamics, and the next, he would be designing instruments to measure them. His laboratory became a sanctuary of precision, filled with thermometers, galvanometers, and delicate apparatus that mirrored his pursuit of accuracy. Every instrument, every equation was a reflection of his belief that nature's secrets could be revealed only through exact measurement. Kelvin's vision of absolute zero was not static, it evolved as science advanced. As the century progressed, new discoveries in molecular theory and atomic physics provided evidence for his ideas. Scientists began to understand that temperature was indeed a measure of molecular motion, and that absolute zero represented a state of complete stillness. Later experiments, using technologies Kelvin could only have imagined, confirmed his predictions with astonishing accuracy. His theoretical boundary had become a measurable truth, validating his genius across generations. The significance of Kelvin's absolute scale extended far beyond physics. It influenced chemistry, engineering, astronomy, and even philosophy. In defining a universal zero point, Kelvin gave scientists a common foundation upon which to build the laws of nature. It was as if he had drawn a line in the cosmic sand, a mark that said, "Here begins the true measurement of reality." This act of defining the unmeasurable turned him from a scientist into a symbol of human intellect. In many ways, the creation of the Kelvin scale was an act of faith, a belief that the universe could be understood, quantified, and expressed in human terms. It embodied the spirit of 19th century science, a time when the world was learning to trust numbers as the language of truth. For Kelvin, this faith was both scientific and spiritual. He saw no conflict between the laws of physics and the presence of divine order. To him, the elegance of the absolute scale was proof of a higher harmony, a cosmic design waiting to be uncovered by reason. As his fame grew, so did his influence. The absolute temperature scale became a cornerstone of physics education, and young scientists across Europe studied his works with reverence. Kelvin himself remained humble, often saying that his discoveries were simply glimpses into the vastness of nature. Yet behind his modesty was a fierce determination, the kind of intellectual courage that changes the course of history. By the time the first absolute thermometers were calibrated, Lord Kelvin had already become a legend in his own lifetime. His scale had transformed how humanity understood heat, cold, and energy. The concept of absolute zero had moved from imagination to reality, from philosophical speculation to scientific law. In the grand story of physics, this was one of the moments when humanity's understanding of the universe deepened profoundly. Kelvin had not merely invented a new way to measure temperature. he had defined a new way to think about existence itself. As Lord Kelvin's absolute temperature scale began to take root in the scientific world, the full weight of its meaning slowly unfolded. It was more than just a new method of measurement. It was a profound redefinition of how humanity perceived heat, motion, and the structure of the universe itself. Kelvin's absolute zero represented an ultimate boundary, a place in nature where all motion stopped, where matter rested in complete stillness. To the imagination of his time, this idea was almost mystical. The thought that there could be a point where energy ceased to exist, where the universe itself would fall silent, was both unsettling and awe-inspiring. Kelvin had not just introduced a new number, he had drawn a frontier between the dynamic and the eternal. In the laboratories and universities of Europe, scientists began to adopt Kelvin's temperature scale, realizing that it offered something the older scales could not: universality. The Celsius and Fahrenheit systems were convenient but human. They depended on arbitrary physical benchmarks like the freezing and boiling points of water. Kelvin's system, however, was cosmic. It could describe the chill of interstellar space as easily as the heat of the sun. It was the same everywhere, untouched by culture or geography. In the simplicity of his zero, Kelvin had given the world a key that unlocked every form of energy transformation, every chemical reaction, every physical process. Kelvin's influence spread far beyond the theoretical. Engineers, inventors, and experimental scientists began using his ideas to develop new technologies. In the growing age of steam, knowing the exact relationship between temperature and energy efficiency was critical. His scale provided the foundation for more precise calculations in thermodynamics, helping to improve engines, turbines, and power systems. The world of industry was unknowingly powered by his insights. As ships crossed the oceans, as factories lit up cities, as machines drove progress, the principles behind their functioning were rooted in Kelvin's understanding of heat and energy. But for Kelvin himself, the absolute scale was also a philosophical journey. He often reflected on what it meant to reach for absolute zero, a place where all motion ends. He realized that even as scientists could approach it mathematically and experimentally, they could never truly reach it. No matter how low the temperature, some residual motion would always remain, as if nature herself guarded that final secret. To Kelvin, this was a reminder of the universe's perfection, a balance between what could be known and what must remain beyond reach. He saw in this limit a reflection of the divine order of creation, a boundary set not by human instruments, but by the very fabric of existence. Kelvin's work on the absolute scale also led him to explore the fate of the cosmos. He realized that if energy could only flow in one direction, from hot to cold, then over immense stretches of time, the universe itself would drift toward a final equilibrium. This was his famous idea of the heat death of the universe, a vision of a cosmos where all stars had burned out, all energy had dispersed, and all motion had ceased. It was a chilling thought, not born of imagination but of thermodynamic law. Yet Kelvin did not view it as despair, he saw it as truth. In the symmetry of that eventual stillness, he found beauty, a universe destined to rest, having completed its grand cycle of transformation. The creation of the absolute temperature scale also changed how scientists viewed the connection between matter and energy. Kelvin's theories suggested that temperature was not a static property but a form of motion, a dance of atoms and molecules vibrating through space. This realization transformed physics forever. It laid the groundwork for later discoveries in molecular theory, quantum mechanics, and statistical thermodynamics. Kelvin could not have foreseen Einstein's work on energy equivalence or the later discovery of quantum zero-point energy, yet his insights formed the stepping stones toward them. His absolute scale became a bridge linking the mechanical world of classical physics to the mysterious quantum realm that would emerge decades later. Kelvin's fascination with measurement drove him to perfection. He built and designed thermometers capable of capturing tiny temperature variations, using gas expansion and electrical resistance as guides, His insistence on accuracy revolutionized experimental physics. Every reading mattered. Every fraction of a degree was a clue to the underlying truth. In one of his letters, he wrote that, "The progress of science is measured by the precision of its instruments." His temperature scale, rooted in that belief, was itself a monument to human precision, a mathematical mirror of nature's laws. As he aged, Lord Kelvin continued to refine his theories, always seeking greater clarity. He worked tirelessly on the mathematical relationships that defined energy transformations, producing equations that described the flow of heat through solids, liquids, and gases. His efforts culminated in the laws of thermodynamics, principles that continue to govern physics, chemistry, and engineering today. He showed that energy could never be created or destroyed, only transformed, and that temperature was the measure of this eternal transformation. His absolute scale became not just a scientific tool, but a symbol of that constancy. Kelvin's contemporaries marveled at his ability to blend deep theory with practical innovation. He was not content merely to define the laws of nature, he wanted to use them to advance civilization. When he helped lay the first successful transatlantic telegraph cable, he applied his understanding of energy transmission to make the project succeed. When he worked on marine compasses and ship navigation systems, he used his knowledge of magnetism and temperature to increase accuracy. For Kelvin, every law of physics had an application in the real world, and his absolute scale provided a foundation for both discovery and progress. Despite his towering intellect, Kelvin remained deeply human. He often described science as a moral pursuit, a way of bringing order to the chaos of ignorance. He believed that truth was sacred, that measurement was a kind of devotion. The idea of absolute zero became, in a sense, his metaphor for purity, the ultimate state of calm, of perfection, of balance. In his writings, one can sense the reverence he felt toward nature's laws, as though he were not inventing them, but uncovering something ancient and eternal. The impact of Kelvin's work continued to grow long after his time. In the early 20th century, as scientists began exploring cryogenics and superconductivity, they found that Kelvin's theories held true even in the most extreme conditions. Experiments brought matter closer and closer to absolute zero, revealing strange new behaviors. Liquids that flowed without friction, gases that condensed into quantum states. Every new discovery confirmed what Kelvin had predicted, that temperature and energy were inseparable, and that the universe's coldest realms held secrets of unimaginable beauty. Today, the Kelvin scale is the foundation of temperature measurement in science. From the calibration of spacecraft instruments to the study of black holes and cosmic background radiation, Kelvin's scale defines the numbers that describe reality. When astronomers speak of the temperature of distant stars or the freezing emptiness between galaxies, they do so in Kelvin's terms. His name, attached to every scientific temperature reading, continues to echo through laboratories, classrooms, and observatories across the world. Yet beyond the numbers, the equations, and the experiments, there remains something deeply human in Kelvin's creation. His absolute scale was born not merely from intellect but from wonder, a desire to find permanence in a universe of change. He gave the world a tool to measure the invisible, to understand the intangible, and in doing so, he left behind more than a scientific legacy. He left a philosophy of precision, a belief that even the coldest truths can reveal warmth when illuminated by curiosity. Toward the end of his life, Kelvin often spoke about the unity of natural laws. He saw in the balance of heat and cold, motion and rest, an elegant simplicity that connected all things. The absolute temperature scale was, for him, a manifestation of that unity, a way to express the harmony that underlies the apparent chaos of the world. He knew that human beings might never touch absolute zero, yet the pursuit of it symbolized something greater, the endless quest for knowledge, the striving toward perfection, the boundless curiosity that defines the human spirit. When he passed away in 1907, his ideas had already reshaped science. His name was immortalized not only in the unit of temperature, but in the very language of physics. Every scientist who measures heat, every engineer who calculates energy, every astronomer who studies the temperature of a star owes something to Lord Kelvin's vision. His absolute scale became a universal constant, a silent tribute to the man who defined the coldest possible point in the universe, and in doing so, illuminated the warmth of human understanding. The mind that defined absolute zero had done more than measure. It had revealed. Through logic, faith, and relentless curiosity, Kelvin had transformed heat from a mystery into a measurable truth. He had drawn the line where the motion of matter ends, and in that stillness, he had found meaning. The universe, once vast and chaotic, became knowable through his numbers. The story of his absolute temperature scale is, in the end, the story of human discovery itself, a journey from confusion to clarity, from ignorance to insight, from warmth to the perfect silence of absolute zero. The concept of absolute zero stands as one of the most haunting and fascinating frontiers in the history of science. It is the point at which all molecular motion theoretically ceases, where the dance of atoms that defines heat, energy, and existence itself comes to an end. For Lord Kelvin, absolute zero was not just a number or an abstract boundary. It was the ultimate expression of nature's precision, the limit of cold that shaped the laws of thermodynamics and the behavior of the universe. He pursued this idea with a visionary's mind and a mathematician's discipline, transforming a simple curiosity about temperature into one of the most profound scientific concepts ever defined. Kelvin's journey toward absolute zero began with his deep understanding of how energy flows. In the mid-19th century, scientists like James Joule were exploring the relationship between heat and work, while others struggled to unify mechanical motion with thermal energy. Kelvin saw beyond the individual experiments. He sought a universal law, a scale that would measure temperature not by human convenience, but by nature's own boundaries. His reasoning was simple yet revolutionary. If heat is a form of energy, then there must be a lowest possible energy state, a temperature where no heat remains to be transferred. This became the foundation of the absolute temperature scale, beginning at 0 Kelvin. To imagine absolute zero is to imagine a world utterly still. At that temperature, roughly -73°C, atoms no longer vibrate in their bonds. The universe would reach a state of perfect calm. For Kelvin, this was not merely poetic, it was a precise mathematical truth that gave meaning to every measurement above it. By defining this baseline, he provided science with a framework that could describe the behavior of gases, materials, and energy under all conditions. It allowed physicists to predict how substances contract as they cool, how entropy behaves as systems lose energy, and how the laws of thermodynamics govern every engine, star, and life form. Yet, Kelvin's brilliance was not in claiming that absolute zero could ever be reached. He knew it was an unreachable ideal, a theoretical horizon toward which temperatures could approach, but never arrive. This understanding gave his theory an almost philosophical depth. It acknowledged the limits of both nature and human ambition. Absolute zero became a symbol of perfection that could be imagined, calculated, and approached, but never possessed. In laboratories centuries later, scientists have cooled atoms to billionths of a degree above absolute zero, watching them move in strange, quantum ways that even Kelvin could only have dreamed of. His legacy thus lives on in the most advanced frontiers of modern physics, in superfluids, quantum computing, and the study of Bose-Einstein condensates. Every time we measure temperature in kelvins, every time a scientist speaks of entropy or thermal equilibrium, they are speaking in the language he created. Lord Kelvin's definition of absolute zero was a triumph of intellect and imagination, a fusion of mathematics, physics, and philosophy. He gave humanity a scale by which to measure the invisible, a way to understand not just how hot or cold something is, but how energy itself flows through the fabric of reality. In his pursuit of the coldest point in the universe, Kelvin revealed something profoundly warm about the human spirit, the endless desire to know, to measure, and to define the limits of existence. Lord Kelvin's contributions to thermodynamics and the principle of energy conservation reshaped the scientific understanding of how the universe works. During an era when the nature of heat, motion, and energy was still shrouded in mystery, Kelvin's analytical brilliance illuminated the hidden laws that governed them. He recognized that energy was not a substance that appeared and disappeared, but a measurable and eternal quantity that simply changed form. This realization became the cornerstone of one of the most important laws in all of physics, the conservation of energy. Through his insights, the physical world began to look less like a collection of disconnected phenomena and more like a finely tuned system governed by universal order. In the mid-1800s, scientists were beginning to unravel the relationship between heat and mechanical work. Experiments by James Joule showed that motion could produce heat, and heat could, in turn, produce motion. Kelvin saw in these discoveries the potential to establish a unified theory that would connect mechanical energy, heat, and the flow of time. He worked tirelessly to refine these ideas into a coherent mathematical framework, which would later form the foundation of the first and second laws of thermodynamics. He realized that while energy could change form, from motion to heat, from electricity to light, it could never vanish or be created out of nothing. This understanding transformed not only physics but also engineering, chemistry, and even the emerging fields of astrophysics and biology. Kelvin's work gave scientific precision to the vague and intuitive idea of force that had dominated earlier science. He turned it into a quantifiable entity, capable of being measured and predicted. In defining temperature and energy mathematically, he provided scientists and engineers with tools to design more efficient engines, refine steam power, and ultimately lay the groundwork for modern energy systems. His interpretation of thermodynamic principles also shaped the industrial age, guiding the development of technologies that powered ships, factories, and communication systems across the world. But Kelvin's genius extended beyond practical application. He was deeply philosophical in his approach to science. The second law of thermodynamics, which he helped establish, introduced the idea of entropy, that energy tends to disperse and that systems move naturally toward disorder. For Kelvin, this was not simply a mechanical truth, it was a reflection of the cosmic order itself. He pondered the fate of the universe, imagining a distant future in which all energy would be evenly distributed, all motion ceased, and no work could be done, a concept now known as the heat death of the universe. Such thoughts revealed Kelvin's ability to blend scientific precision with profound existential vision. His theories also influenced the understanding of equilibrium and reversibility. Kelvin showed that no process in nature is perfectly efficient. Some energy is always lost as heat. This insight changed how engineers designed machines and how scientists viewed natural systems, emphasizing that every transformation comes at a cost. His insistence on measurement and numerical accuracy pushed experimental science toward a new standard of rigor, one that would define modern physics. Even as new discoveries in quantum mechanics and relativity emerged in the 20th century, Kelvin's thermodynamic principles remained unshaken. They still govern engines, stars, and the smallest particles of matter. Every chemical reaction, every transfer of heat, and every movement of energy in the cosmos follows the framework he helped construct. Lord Kelvin gave humanity not only the laws of energy, but also a way to see the universe as a grand, interconnected system, one in which nothing is ever wasted, nothing ever disappears, and everything moves according to immutable principles. Through his work, Kelvin bridged the gap between the seen and unseen forces of nature. He transformed energy from a mysterious concept into a measurable reality. His legacy is not confined to equations or laboratory experiments, it lives in the very structure of our modern world. Every machine that moves, every current that flows, every star that burns, and every living being that breathes owes its existence to the laws he helped define. Lord Kelvin's contribution to thermodynamics and the conservation of energy is a testament to the enduring power of human curiosity. To understand, to calculate, and to uncover the timeless order within the chaos of nature. Lord Kelvin was not only a visionary physicist, but also a pioneering engineer whose mind bridged the gap between abstract theory and real-world innovation. His understanding of mathematics and thermodynamics gave him a unique ability to apply scientific knowledge to practical problems, particularly in the age of industrial progress and global communication, where many scientists of his time confined themselves to laboratories and equations. Kelvin ventured into the world of invention, engineering, and maritime exploration. He believed that true science was not only about discovering the laws of nature, but also about using them to improve human life. Through his engineering brilliance, Kelvin became one of the driving forces behind the technological transformations of the 19th century. One of Kelvin's most remarkable achievements was his contribution to the laying of the first transatlantic telegraph cable. During this period, communication between Europe and America relied entirely on ships, taking weeks for a single message to travel across the ocean. The idea of transmitting electrical signals through an underwater cable spanning thousands of miles seemed impossible to many engineers. Early attempts had failed because the signals weakened as they traveled, distorted by resistance and capacitance within the cable. But Kelvin's deep understanding of electricity and magnetism allowed him to see the problem in mathematical terms. He analyzed the flow of current through the cable and developed formulas to predict how signals behaved over long distances. His calculations not only explained the failures of earlier efforts, but also guided the design of new, more reliable systems. Kelvin invented sensitive instruments such as the mirror galvanometer, which could detect the faint electrical signals arriving after their long journey through the ocean floor. This device used a small mirror and beam of light to amplify tiny deflections caused by the incoming current, allowing operators to read messages that would otherwise have been invisible. The success of this invention was a turning point in human history. In 1866, when the first successful transatlantic telegraph cable was completed with Kelvin's help, it revolutionized global communication. What once took weeks now took mere minutes. Nations, businesses, and families could exchange messages across continents almost instantly. It was one of the first steps toward the interconnected world we know today. Kelvin's engineering vision went far beyond communication. He applied his understanding of thermodynamics to design more efficient engines and improve the performance of steamships. His inventions in navigation, such as the Kelvin compass and the tide predictor, became essential tools for sailors and explorers. The tide predictor, a mechanical analog computer, could forecast tidal patterns with great accuracy, saving countless ships from disaster and enabling safer global trade routes. Kelvin's compass was designed to remain steady even when surrounded by the iron hulls of modern ships, a problem that had confounded navigators for years. These practical contributions demonstrated that his scientific insights were not limited to theory, but extended into the very heart of technological progress. Despite his fame as a physicist, Kelvin often described himself as an engineer at heart. He believed that science reached its highest purpose when it served humanity. His work on temperature measurement, thermodynamics, and electricity found real application in the technologies that powered the Industrial Revolution. Factories, engines, and communication systems all bore the mark of his influence. He showed that science was not just about understanding nature, but also about mastering it to create tools that advanced civilization. Kelvin's engineering achievements also reflected his character: meticulous, disciplined, and visionary. He demanded precision in everything he built, testing each design until it met his exacting standards. He often worked directly with technicians and sailors, solving problems on site rather than from a distance. His presence aboard cable, laying ships became legendary. He would spend nights calculating improvements, adjusting instruments, and ensuring every signal was clear. To many, he was the embodiment of the union between intellect and action, a man who could dream in equations and build with his hands. Through his engineering innovations, Lord Kelvin helped shrink the world. He turned abstract knowledge into tangible power, linking continents and changing the rhythm of human communication. His inventions made science visible in everyday life, proving that the invisible laws of physics could be harnessed to connect hearts and minds across oceans. Kelvin's work stood as a testament to the idea that progress is born not only from thought, but from the courage to transform ideas into reality. He left behind not just theories and equations but machines, instruments, and technologies that carried his genius across generations. Even today, his name resonates wherever precision, innovation, and the spirit of discovery define human endeavor. Lord Kelvin's legacy stands as a symbol of precision, intellect, and the relentless human pursuit of understanding the universe through measurement and reason. His name, forever attached to the Kelvin temperature scale, is more than a scientific unit. It is a monument to a man whose mind sought order in the invisible forces of nature. Kelvin believed that knowledge must be grounded in numbers, that true science begins only when observation can be quantified. His famous words, "To measure is to know," became the guiding principle of modern physics, engineering, and technology. This devotion to accuracy not only defined his own work, but also set the foundation for generations of scientists who followed, transforming how humanity explored and comprehended the natural world. In an age when many scientific ideas were still shaped by speculation, Kelvin insisted that every theory must stand upon measurable evidence. He transformed physics into a discipline of exactness, where even the unseen could be described through mathematics. His careful calculations and insistence on verification elevated science from a philosophical pursuit into a practical tool for understanding reality. To Kelvin, precision was not a limitation. It was a form of beauty. He found elegance in numbers, in the harmony of physical laws that could be expressed through equations. This belief guided every discovery he made, from the laws of thermodynamics to the measurement of electrical signals and the properties of energy. Kelvin's influence extended beyond laboratories and classrooms. It reached into the heart of the industrial age. Engineers, inventors, and explorers turned to his principles to design machines, build ships, and create instruments that reshaped civilization. He proved that mathematics could not only describe nature but also command it. His insistence on rigorous measurement led to advances in navigation, communication, and energy production. Every calculation he made, every formula he refined, carried with it a sense of responsibility, an understanding that precision was not just for science, but for progress. But Kelvin's legacy was not confined to his instruments or equations. It lived in his spirit of inquiry. He saw science as a lifelong journey, one driven by curiosity and humility before the vastness of the universe. Despite his brilliance, he never considered knowledge complete. He believed that every answer opened the door to deeper questions. This humility gave his work a timeless quality. He inspired others to look beyond the visible, to measure what could not be seen, and to trust that truth could always be found through careful observation. Even in the twilight of his life, Kelvin remained a symbol of intellectual vigor. He continued to teach, invent, and question until his final years, leaving behind an unshakable standard of excellence. His name became synonymous with accuracy and scientific integrity. The Kelvin scale, used universally in physics and astronomy, reflects not only his mathematical genius, but also his vision of an ordered, measurable universe. In laboratories across the world, every time a temperature is recorded in kelvins, it echoes the precision of the man who defined absolute zero and gave meaning to the very concept of measurement. Kelvin's work also carried a deeper philosophical resonance. By defining the limits of temperature and energy, he revealed the limits of human understanding, and in doing so, expanded it. He taught that nature's laws were not barriers but invitations to explore. His scientific vision became a metaphor for the endless quest for truth, reminding humanity that knowledge is both a discipline and a wonder. The same mind that measured the invisible also understood the poetry of discovery. the quiet beauty found in a perfect equation, a precise experiment, or the stillness of absolute zero. Today, Lord Kelvin's legacy endures in every scientific field that values precision, from quantum physics to space exploration. He set the benchmark for what it means to truly understand the world, not through guesswork or belief, but through observation, calculation, and proof. His life's work became a bridge between theory and practice, between the infinite vastness of the cosmos and the human ability to comprehend it. He taught that measurement is not just a method, but a language. The language through which the universe speaks to those who are willing to listen carefully. Lord Kelvin defined more than absolute zero. He defined the essence of scientific pursuit itself. His legacy is etched into the instruments that measure light, the engines that power ships, and the formulas that describe the stars. He remains a symbol of disciplined curiosity, a mind that found meaning in precision, and a thinker who measured not just the physical world, but the depth of human intelligence. Through his work, he gave science its most enduring gift, the conviction that the truth of the universe can be captured, understood, and shared through the unwavering clarity of numbers.